For centuries, the idea of reversing aging belonged to the realm of myth and science fiction. We've pursued youth through lotions, diets, and lifestyle changes. But all of these have only ever addressed the symptoms of aging, not the root cause. But what if aging itself isn't an inevitable, irreversible decline? What if, deep within our cells, the biological clock could be turned back? Today we're exploring one of the most exciting and promising frontiers in modern science, the theory of cellular reprogramming. Scientists are now investigating whether we can reset our cells to a more youthful state, not by changing our DNA, but by altering how that DNA is read. This is the promise of epigenetic reprogramming, a radical new approach that suggests aging might not be a one-way street after all. To understand reprogramming, we first need to understand a key concept: the epigenome. If our DNA is the hardware, the fixed set of instructions that makes us who we are, then the epigenome is the software. It's a complex system of chemical tags and modifications that tell our genes when and where to be active or silent. This is how a skin cell and a brain cell, which have identical DNA, can perform such different functions. As we age, this software becomes corrupted. We experience what scientists call epigenetic drift. DNA methylation patterns change. Histones, the proteins that package our DNA, shift, and our cells lose their precise, youthful gene expression patterns. This breakdown in the information that governs our cells is now considered a central driver of aging. It leads to cellular senescence, where cells stop dividing and become dysfunctional, and a decline in our body's ability to repair and regenerate itself. This is where the theory of reprogramming comes in. The idea is to use specific proteins or molecules to clean up the corrupted software, restoring the youthful epigenetic landscape without erasing the cell's identity. This is known as partial or transient reprogramming. The foundation of this field was laid in 2006 by Nobel laureate Shinya Yamanaka, who discovered a set of 4 factors: OCT4, SOX2, KLF4, and c-MYC, now known as the Yamanaka factors, or OSKM, that could revert an adult cell back to a pluripotent stem cell state. This was a full reset, wiping the cell's slate completely clean and making it capable of becoming any cell type in the body. While revolutionary, full reprogramming is too dangerous for simple rejuvenation, as it carries a high risk of cancer. The breakthrough came when researchers realized that short, temporary exposure to these factors could reverse some signs of aging without erasing the cell's identity. This cyclic approach, for example, 2 days on and 5 days off, has been shown to rejuvenate cells and even extend the lifespan of mice. But it doesn't stop there. The field is rapidly evolving beyond the original Yamanaka factors. Scientists are now developing safer and more precise methods, including mRNA-based delivery, delivering the reprogramming instructions as temporary messages that don't permanently alter the DNA. CRISPR-A, using a modified CRISPR system to gently turn on the body's own rejuvenation genes. Chemical cocktails, developing small molecules that can achieve the same rejuvenating effects without any genetic modification. Recent research has been nothing short of remarkable. Studies have shown that partial reprogramming can restore vision, improve muscle and liver function, rejuvenate skin, and reverse senescence markers across multiple organ systems in mice. It works by calming the inflammatory SASP response of senescent cells and restoring mitochondrial function, effectively helping old cells act young again. So, Can we reverse aging? The answer is a cautious but resounding maybe. The science is powerful and the proof of concept is there. However, the journey from mouse models to human therapies is fraught with significant challenges. The biggest hurdle is safety. There is a very narrow therapeutic window for these interventions. Apply too little and nothing happens. Apply too much and we risk tumor formation or the loss of cell identity. We also don't fully understand the long-term effects of a treatment that affects the software of nearly every cell in the body. Yet the future is incredibly promising. Researchers are now using AI and single-cell technologies to map the precise molecular dynamics of rejuvenation, moving us closer to predictable and safe therapies. The dream is to move beyond treating individual diseases like diabetes or heart failure and instead tackle the fundamental process that makes us susceptible to them in the first place. This is the ultimate goal of longevity science: to extend our health span, the number of healthy, disease-free years we live, by addressing the root cause, aging itself. We are, perhaps, at the dawn of a new era in medicine, one where we don't just treat disease, but intervene in the aging process itself. Thank you for listening.